Hey guys, just wanted to share real quick here another sort of definition of conservation of momentum and how we get there. So, um, here we have, let's say, a gun and a bullet. And so we're going to fire it. The gun is going to push on the bullet, and the bullet is going to push on the gun. So the question is, who pushes with more force, the gun on the bullet or the bullet on the gun? Well, those are equal but opposite forces there. How do we know that? That's according to Newton's third law, right? For every action, there's an equal but opposite reaction. So next question is, who pushes for a longer time, the gun on the bullet or the bullet on the gun? Well, those are also going to be equal. Why? Well, it's just logical. The gun can't be in contact with the bullet without the bullet being in contact with the gun. So, third question here. If they push on each other with equal but opposite forces for equal times, what else by definition must be equal? What is force times time? Well, from 2 weeks ago, we learned that force times time is impulse. So they must have equal but opposite impulses. Next question here is, if they have equal but opposite impulses, what else must be equal but opposite? What else is impulse equal to besides force times time? And that's changes in momentum. We learned that from the impulse momentum theorem, that impulse is force times time, but it's also equal to a change in momentum. So equal but opposite changes in momentum. And here is sort of the conclusion of it all. If the gun and the bullet are the system, so the system is just the collection of objects that we're looking at. We could just be looking at the gun, we could just be looking at the bullet, but in this case, we're looking at the gun and the bullet together. So they're our system. So what's the overall change in momentum of the system? It's got to be zero. Why? Well, whatever the change in momentum of the bullet was, we just said the gun has an equal but opposite change in momentum. So those two things cancel each other out. So if we think about it, let's say in this case, the momentum of the system before was zero. That means the momentum of the system afterwards has to be zero. But if the gun and the bullet were moving beforehand and had 10 units of momentum before, they'd have to have 10 units of momentum afterwards. So, and that again is because the momentum cancel. Remember that left indicates negative, and so that's normally how we're going to make it work out here. So let's say here in this case, we had a gun with a mass of 4 and a bullet with a mass of 0.01, and we fired that bullet with a velocity of 300 meters per second. We could figure out the velocity of this gun. We've already basically done this. We know this because their momentum got to be equal but opposite. By the way, the gun, most of its momentum is in its mass, and the bullet, most of its momentum is in its velocity here. So we could figure out the momentum of the bullet, take its mass, 0.01, times its velocity, 300, and you'd get 3. So the momentum of the bullet is 3 now. Before it was 0, now it's 3. So that means it changed by 3. That means the gun has to change by -3. And so we could figure out its velocity by taking its mass divided by its velocity there, or its velocity divided by its mass. And then we could get 0.75. So let's sum it all up here. So the law of conservation momentum, what does it say? When there's no net outside forces on a system, the momentum is conserved. That's important. No net outside forces. So if our system was the bullet, it had an outside force on it, the gun. So its momentum can change, obviously. The gun has an outside force on it, the bullet. So its momentum can change. But if our system is the gun and the bullet together, then there's no outside forces. They're all internal, and therefore the momentum can't change. In mathematics, we would sum this up by saying the net momentum before the collision is equal to the net momentum after the collision. Or if we want to write it as simply as possible, P equals P prime. Momentum before is momentum afterwards. So in our problems then, we expanded this. We only have 2 object systems. You could have more, but we're going to keep it to 2. So momentum of object 1 before plus momentum of object 2 before is equal to momentum of object 1 afterwards plus momentum of object 2 afterwards. Or substituting in for each of those, how do you find those? Mass 1 times velocity 1 before plus mass 2 times velocity 2 before is equal to mass 1 times velocity 1 afterwards plus mass 2 times velocity 2 afterwards. Whew, that's a lot. All right, let's stop this now.